Hello everybody, my name is Mustafa and this is my presentation on the summary of the paper Dynamic Graph CNNs for Learning on Point Clouds. Point clouds have become very common in computer vision due to their increase in the camera accuracy and the expensiveness of point cloud cameras in the past few years. But point clouds are not inherently the same as 2D images. And so although CNNs have become very popular and very strong for processing 2D images, applying that type of processing to point clouds remains a key challenge. The paper Dynamic Graph CNNs tries to achieve CNN-based performance and features on the idea of on point clouds. And how this is accomplished is that the point clouds are transformed into graphs. And once you turn into a graph, then you can take the principles of convolutions and apply them to the graphs themselves. And so this work extends previous work done by PointNet, but extends it in a way that local geometric information is also incorporated. And this is done through graphs. And this operation of graph convolutions can be applied repeatedly and has good effect and interesting results, especially in regards to creating semantic relationships between groups of points, even if their Euclidean distance is large. It also achieves state-of-the-art performance on classification and also achieves strong results in part segmentation. A bit of background before going into the architecture of the network. CNNs have existed for many years now, and the principle behind CNNs is that you take a small patch of your 2D image and you apply some type of kernel or filter. And through this operation, you're able to accumulate a feature map of that image. Using multiple filters, you're able to accumulate multiple feature maps. And so you're able to gather local pixel information and aggregate it to achieve some types of feature processing. And so the same concept can be applied to graphs. If you take the nearest neighbors of a certain point in a graph, then convolutions can also be applied to the graph itself. And what this does is that you aggregate the information from local neighborhood points and you aggregate it onto the point itself, and this creates a feature point which is essentially aggregates the information of the local neighborhood points. And in a broader architectural setting, this type of convolution can be applied in similar ways to the convolutions in 2D images, where you apply the convolutions to achieve some type of feature maps, and you pool the information to aggregate the data. And you continuously apply this type of convolution until you reach the very end, where you can apply typical MLP style layers and achieving classification at the very end through a softmax. And so in this paper, what happens is that you have an input point cloud, and the paper introduces the idea of learning local edge embeddings of points. So given a point xi and the nearest neighbor points xj, you learn a network parameters h using the function h, where you're trying to learn the edge embeddings. And after you learn the edge embeddings, you can aggregate the edge embeddings back towards the point xi. And so what this architecture is going to accomplish is that each input point cloud is going to find local points and you're going to be able to apply convolutions and aggregate the results. And so in the overall architecture, what happens is that there are two main aspects. The first is what we've already seen in architectures such as PointNet, and that is the idea of a spatial transform. And so the spatial transform takes the input point cloud and converts it into a canonical pose. And this, as proven in PointNet, is very important for standardizing or normalizing the point clouds. And this point normalization is done through creating a k-nearest neighbor graph and estimating a 3x3 matrix that will allow you to convert your point cloud to a canonical pose. After that, there's a series of edge-conv operations. And these edge-conv operations take the principle that you're going to construct a k-nearest neighbor graph. And from that k-nearest neighbor graph for the points, you're going to apply your convolution operation and pull the results back in, or aggregate the results. And through successive operations of edge-conv, you're able to extract information from local points. And as you get higher up in the layers, then the semantic points get pulled further, closer and closer together. And so the idea here is that in higher layers, the semantically closer points, so semantically similar points, will actually be closer in feature distance. And here they have two separate architecture branches. One of them is specifically designed for classification, and another one is designed for segmentation. And the main difference here is that you'll notice the concatenation happens in different areas in both cases. But the overall idea is that for classification, you're going to output a single classification score for the different classes, whereas for segmentation, you're going to have a per point classification. For results, we noticed that this network achieves state-of-the-art performance in classification. But the interesting thing here is that the state-of-the-art results, when you compare it with the size and speed of the network, is actually extraordinary, impressive. You'll notice that the size of the model and the time for inference is actually very small compared to PointNet++. And so we achieve state-of-the-art performance while also keeping a very small model size. Some results on part segmentation, you'll notice that compared to PointNet, the parts themselves are very clearly defined, and the edges are very clear here, and there's no overlap or bleed. When we look at the results of the part segmentation for accuracy, we notice that although there is not state-of-the-art in every category, we still have the same efficiency and the same speed gain. So we do achieve comparable results to state-of-the-art, but maintaining the high speed and low model size. Some results on indoor scene segmentation. You'll notice again that compared to PointNet, the segmentations are very clear, the edges are very well defined. Some interesting results you'll notice is that distances in feature space actually show that as you get farther into the network, so here you'll notice that 3 columns are later stages of the network, that semantically similar things get closer to and closer in feature space. And this can actually be seen as well across different point clouds. So here you'll notice that taking a point cloud A and a point location as seen by the red orb, even in very different point clouds, if you can actually compare distances in feature space and find similar point groupings in completely different point clouds. And so overall, we can notice that the principles of convolutions can be applied to point clouds by transforming the point clouds into these local graphs. The local information is captured in these local graphs. And the two interesting results that we see in this paper is that across large distances, we're still able to get semantic groupings. So semantically similar parts of the object will actually have closer distance in feature space in later layers. We're also able to transfer those same distances in different point clouds and see the same semantic groupings. Some critiques or limitations. The explanation of why the state-of-the-art is not achieved in the part segmentation is not clear, although we can probably guess that this has to do with the small model size compared to what the other models might be using. By focusing on edges, though, one clear limitation is that the relative positioning of the points themselves is sort of ignored or lost. And so we can also look at this from a different angle, and we can say that we're also ignoring the deformations of local patches. And we also don't know exactly if the relationships in high-level feature spaces is robust or not. And this hasn't been answered accurately. So overall, to recap, this paper learns high-level information from point clouds, and specifically we apply the idea of convolutions to point clouds. Prior work did not incorporate local information in geometry, but by using graphs we're able to gather this local information. And we're able to dynamically reconstruct the graph to produce strong results.